Today, I came here by car. While I was driving, I sent out a lot of messages, like really a huge amount of messages. It is known that it is really dangerous to drive and text at the same time, but I don't feel ashamed, not at all. Do you want to know why? Because I wasn't texting and I did not send those messages directly. I just made my car doing this. In a modern car, every electronic component can be considered as a little computer. Can you guess how many little computers can be found in a brand new car with like full extras? Well, the answer is around 200. And all these little computers have to communicate with each other on the in-vehicle network of the car. And by the way, seriously, don't text and drive. These statistics look scary. Hello, everyone. Let me introduce Julia, who works with us as a security research intern, and she was the one who implemented our solution. A few words about me. I'm David. I work as a security test engineer for Bosch, and I was assisting Julia with ideas during the development of this tool. Okay, guys. Who saw the movie The Matrix Reloaded? Raise your hands if you have seen it. Who think it was a versus sequel of the first episode, or the first one? Interesting. Okay. Anyway, in this picture, you can see Trinity use the CANmap for hacking the power grid of a city. For those who don't know CANmap, it is a network scanning tool which operates with active network scanning ability. This means CANmap sends messages to its target, and from the received answers, it draws conclusions. Stick to the matrix example. With the help of this tool, Trinity was able to identify her target on the network. She was able to identify the running services on her target, and she was able to notice that a certain SSH server, what her target was using, was vulnerable to an exploit, and she could execute this exploit. So if you ask me, CANmap is a really powerful tool. But why am I talking about CANmap when my topic is the vehicle industry? Because Ethernet nowadays is widely used in cars. And yes, from the data link layer, it is the exact same Ethernet that the one which we use, for example, in our home computer networks. Only the physical layer got modified a bit to be more fault tolerant. This means that if we want to pen test a car or some vehicle electronics, we can use CANmap on its Ethernet communication channels. But there are other types of networks in the car, for example, CAN, LIN, FlexRay. What can we do with them? For that, we can't use CANmap. So let's make a CANmap which is able to scan on CAN networks also. Our aim with making the CANmap tool was to develop a proof of concept tool which shows the possibilities of automated network scanning in case of CAN, aka Contra Arena network. A few words about the CAN network itself. As you can see, its data structure, its frame structure is quite similar to Ethernet's. CAN frames are transmitted on the network really simply with the differential signal on two voltage levels. One of them indicates a 1, while the other indicates that a 0 was transmitted. This network is completely broadcast, which means if one node starts transmitting a message, then it will be seen by all the other nodes who are connected to the network. Like in case of every broadcast protocol, it is really important how we handle collisions. In case of CAN, collisions are handled by avoidance with the help of the ID field as the following. If two nodes start transmitting their message at the exact same time, the one with the lower message ID value will win the arbitration itself. I said CAN is quite similar to Ethernet, but there are a few key differences. The first of them, in CAN, you can't find any source or destination address, only the message ID, which identifies the message itself, not the sender, and of course it is used for the arbitration. The other big key difference is that in a CAN message you can put maximum 8 bytes of data, so it is much smaller than an Ethernet frame can be. To make it easier to imagine how this network works, let's assume that the communicational nodes on the network are people like Alice, Bob, or Eve, and the network itself is a dark room. In this dark room, we can hear every conversation. So if Alice is talking to Bob, Eve surely can hear it and listen it. we also have to assume that we don't know which direction the voices are coming from. And of course, we can't see who is talking because this is a dark room. In this network, it is also true that if one node wants to imitate another node's voice, he can or she can surely do it. So if Alice asks something on Bob on the network and waits for Bob's answer, if this answer is coming from Eve, Alice just won't notice the difference. And now Yuli will introduce the details of our solution.
Well, hello. We have already introduced ourselves, but I would like to introduce the other participant of the project. But you can see in the picture by my best friend in the last couple of months, the electronic control unit, shortly ECU, to which I spoke and who not only listened, but also answered like a real friend. Basset, the dog, the master of debugging, and the standard, huge amount of standards, which are useful because almost all of the electronics meet these requirements. And finally, the tool itself. An important consideration was that the tool shouldn't have prior information about the CAN channel and the node it is investigating. So it could be used in various situations as a black box testing tool. I implemented it in Python with the help of Pandas and with the base of Python CAN. Pandas is a software library written for data manipulation and analysis. Python CAN is an adapter library which provides the capability to send and receive messages on CAN network. My program is made of independent passive and active modules. The first thing I will talk about is passive section, where the aspect is not to send any message, only listen on the broadcast network. This module is responsible for monitoring incoming messages, checking the period time in case of cyclic messages, and if something doesn't arrive, it is logged. Cyclic messages are very typical in vehicle communication. For example, speed sensor periodically reports speed to other devices. You can see in the picture the message ID, the period time, the timestamp, and the data itself. With help of a line column, you can easily notice if a cyclic message transmission stopped. This module can also identify the channel type. This is the only point where the device may send a message during passive scanning in a channel if the channel type cannot be identified with only sniffing. Let me introduce you the most important CAN-based protocol in automotive and industry, ISOTP and UDS. ISOTP messages are encapsulated into CAN frame similarly, while IP messages are put into the payload part of an Ethernet frame. ISOTP handles communication in network and transport layer. It has two really important benefits. The first, with help of ISOTP, we can send data which doesn't fit into one simple CAN message. We split the data into small pieces with ISOTP and send it with multiple messages. The second, with help of ISOTP, we can address the communication nodes on the network. UDS stands for Unified Diagnostic Service. It is a collection of useful services. For example, this is used by car mechanics to read out error messages from a failed car component. It also has security-relevant service. Like with UDS, we can reset ECUs, read out or modify its firmware. This function had to be protected with a secure session, which means we put the ECUs in secure state with an authentication process. As you can see, ISOTP has several frame types and addressing mode. Some address mode use ID field of CAN message, while others use the data part too. To be exact, there are 4 different frame types and 7 different addresses mode. It's a little complicated. Anyway, you don't have to know this stuff because our tool does. During passive scanning, it can recognize and log every useful ISOTP and UDS parameter, which later can be used in other modes. After executing a passive scan, we cannot be sure that our tool identified all of valid ISOTP addresses on the network. That's why we have an active scan for that. This model uses the most basic command on the Unified Diagnostic 021001, which means in the language of standards, please enter diagnostic session control default session mode. This message sent to all possible addresses in case we receive an answer, receive the address because later we can communicate it to target with it. This brute force can be done a few minutes. I like this video of it. It's a really meditative. After gathering the active addresses on the network, we can examine them one by one. When I say the word session, probably something else comes to your mind, for example, session hijacking, but it's completely different. In case of UDS, sessions are states in which the devices can be sent to these states and define which services are usable on the device at the moment. By entering each session, we check which are available. With this method, we can build a directed graph. As you can see on the picture, where every number refers to a different session mode. The tricky part is that not all services are available from all the sessions. This is the next step that our tool can check in an automated way. As you can see in the table, the security-relevant services are protected with an authentication process. For example, with the read memory by address, we can read out the whole firmware of the device. That must be protected. The authentication itself goes as the following. We send a request to the ECU. As a response, it generated and sent back to a random seed. It generated and sent back. Parallelly, with a shared secret, we combine the seed into a magic value, which is our response. Sometimes this shared secret means only a bit shifting on the seed itself. When we send the response value back to the ECU, it's compared it with its own calculated response and decide whether this equals or not. When it does, we have a positive response and enter successfully in a requested session. And we are happy. We had the opportunity to test the tool live. It was an interesting experiment to see on my laptop what happened inside a real car in motion. During this test, we made a lot of logs. After the real car test, it was interesting to compare the real logs with the one which we made during a simulation we used in development. This was awesome. I'm really waiting for the next one. Now David will show you the attack possibilities on CAN.
Yeah, I'm back. So if we want to eavesdrop on the network, it is easy as a piece of cake because I already told you that this whole network is broadcast, so we can just hear every conversation. Due to the small message size of CAN, it is really hard to do some proper encryption on it. Also, if we want to send out some fake messages, it is also really easy. Once we are connected to the network, we are able to craft any type of message we want, so we can inject anything. Also, as you can see in the picture, if Eve starts shouting all the time, we won't be able to have a nice conversation in the dark room. So flooding the network is really easy. If we start sending constantly a message with the lowest message ID possible, we just always win the arbitration, and the other ECUs on the network won't be able to communicate. There are some not so obvious damage scenarios also. For example, let's assume I'm driving on the highway and there is a node on my car's network which was hacked. For example, I'm driving with high speed and this hack node sends out a please open the airbag message. I won't be happy about it, and a huge accident can be caused like this. Also, while we were testing our tool on real ECUs, we saw some surprising behavior. For example, one body control module we tested, when we sent it to programming session, which doesn't need any type of authentication, it just completely stopped communicating. Much more damage can be caused with a device which is able to disturb the CAN network itself in the physical layer. With a device like this, we can interrupt bits of a message which is already sent out on the network at the moment by some other node. Of course, this will be noticed by that node, and this will send an error message. If we do this constantly on the network for a short period of time, then the nodes will enter into bus-off behavior mode, which is a mode which was established to handle misbehaving ECUs. Once they are entered to bus-off behavior, it means they are just completely disconnected from the network. In theory, it is possible to make an attacker device which splits the whole CAN network into two subnetworks, like subnetwork A and subnetwork B. For Alice to don't see that something went wrong, she has to communicate with Bob also, who is at the moment on the other subnetwork. So Eve, the attacker device, has to provide some gatewaying between the two subnetworks. But this also means if Alice sends out a message, she sees it correctly on the first subnetwork, but then it can be modified by Eve on the second subnetwork, and Bob will receive in the current time from Alice a message which wasn't sent by Alice. This way, a man-in-the-middle attack can be accomplished. In the future, we would like to do more real car tests. I hope we will have the opportunity. In my opinion, this was the most fun part of the whole development and testing process of this tool. And also, we would like to implement more scanning ability of more protocols which are CAN-based. For example, XCP, which is a calibration protocol widely used in automotive industry, would be a nice choice, in my opinion. And we would like to use this tool in case of real penetration test projects.